Good morning everyone. So in the previous class we have gone through the Jablonski diagram. In the Jablonski diagram we have discussed the possible deactivation processes, the different molecular structures and the chemical environment through which a substance may fluoresce will be discussed in this particular class. In the Jablonski diagram, we came across various wordings like intersystem crossing, we came across like external conversion, internal conversion, there was fluorescence, phosphorescence, there were words like radiational-less transitions and radiation transition. And finally, we could decide upon when a fluorescence shall happen and when a phosphorescence shall happen. Based on this system, now the next concept in this particular chapter shall be variables affecting fluorescence, phosphorescence, in common it is luminescence. Molecular structures and the chemical environment influence whether a substance will fluoresce and the intensity of these emissions will be decided. Now this is dependent on these type of systems, or it is dependent on these variables. Now these variables can be quantum efficiency, transition types, structure and structural rigidity, temperature, solvent effects, effects of pH, effects of dissolved oxygen and concentration effect. So let us see first one. It is called as quantum yield or quantum efficiency. It is represented by phi. The quantum yield or quantum efficiency, it is used to measure the probability of a molecule to fluoresce or phosphorese. That means whether a molecule will be fluorescing or phosphorescing. Now for fluorescence and phosphorescence, this particular ratio that you can see upon the screen is the ratio of the number of molecules that are luminescent to the total number of molecules that are excited. Now for highly fluorescing molecules, the quantum efficiency should approach 1, that is phi is equal to 1. Molecules when phi is equal to 0, then they will not fluoresce. The quantum efficiency phi for a highly fluorescent compound like fluorescein can be seen, and it is 1 under some conditions. Now phi is equal to, it is the ratio of Kf divided by Kf plus Ki plus Kec plus Kic plus Kpd plus Kd. Now these are nothing but Kf is the rate constant of fluorescence, Ki is the rate constant of intersystem crossing, Kex is the rate constant of external processes, Kin is the rate constant of internal processes, Kpd is the rate constant of pre-dissociation, and Kd is the rate constant of dissociation. Now the deactivation processes, when they include all these systems, now when I say they are related by the quantum yield equation. Now generally when I say that this particular quantum yield equation is given, so my phi should always be nearing 1 for a particular molecule to fluoresce. If this has to happen, that means the denominator should have as less value as possible. That means intersystem crossing, external conversion, internal conversion, pre-dissociation of the molecule and dissociation of the molecule should be as least as possible. Then only the Kf or the phi will approach 1, and then only the molecule will fluoresce. This is an example of fluorescein isothiocyanate, where we can say that this particular molecule is highly fluorescing molecule because its phi is almost approaching equal to 1. So the first one is quantum yield or quantum efficiency. The second type is called as transition types. Now Fluorescence rarely results from absorption of ultraviolet radiation of the wavelength shorter than 250 nanometer because radiation at this wavelength has sufficient energy to deactivate the electron in the excited state by predissociation or dissociation. Now, why is the consideration of more than 250 nanometer is because generally the molecule shall dissociate. Now, for example, if I take up iodobenzene and I shine a light of less than 250 nanometer, then the iodine easily dissociates off and then the fluorescence cannot be observed. Hence, generally it is always seen that 250 nanometer greater than that, the transition types will be taking place. That is, the wavelength used should always be more than 250 nanometer. The bond of some organic molecules would rupture if it is less than 200 nanometer. That means the bonds will rupture off and we will be getting some kind of denatured compound. If I am considering say bromobenzene, I might not get bromobenzene at all. I might just get bromide and I might get just benzene, and the fluorescing molecule may not happen at all. For this same reason, sigma to sigma star transition, the fluorescence are rarely observed. Instead, the emissions from a less energetic transitions will occur. Now, these less energetic transition can be pi star to pi or pi star to n. When do we observe pi star to pi? When there are n number of conjugated double bonds, or when there are lone pair of electrons, we can say where we can observe pi to pi star. Obviously, when we are speaking about emission spectroscopy, we can observe pi star to pi, n to pi star. We can say that there is a shorter life of fluorescence, that is 10 raised to minus 7 to 10 raised to minus 9 second. Now, this is due to pi star to pi, that means returning from an excited state to the ground state. Longer life for phosphorescence, that means 10 raised to minus 5 to 10 raised to minus 7 second, where pi star to n. This happens because we have already seen this is due to intersystem crossing. Now, fluorescence is most commonly found in compounds in which the lowest energy transition is pi to pi star. That means obviously I should say that it is having the lowest transition, that is absorption. Now, what is an emission? Pi star to your pi system, or it can also happen in the state of n to pi star. So, what is an emission system? It should be pi star to n. So, in this way we can consider that the transition types that are involved in the fluorescence and phosphorescence to happen, that is to get a radiation transitions to happen, are either pi star to pi or pi star to n. Now, if I want to understand what is a phosphorescent quantum efficiency, it is an opposite of fluorescence. That means it has to first undergo an intersystem crossing. That is, first it has to go from singlet to singlet, singlet to triplet state. From there, triplet state, again it has to return back to the singlet state and back to the ground state. Now, that is your phosphorescent quantum efficiency. Now, intersystem crossing is also more probable when there is pi to pi star excited state than for n to pi star state, because the energy difference between singlet and triplet state is large and spin orbit coupling is less likely to occur. Now, what I can say that phosphorescence can only happen if there is an intersystem crossing. That means this intersystem crossing should be in such a way that the energy gap should be very less. So, what are the transition types that we consider? They are pi star to n or pi star to pi. It can never be sigma to sigma star or sigma star to sigma. This is because the wavelength required for sigma star to sigma is very high, and this causes a dissociation or pre-dissociation of the molecule. Now, this is about the transition types involved in the variables. Now, these two are the examples where I can say these are some kind of dyes. Now, they are Fura 2 and Indo 1. Now these dyes, they speak about, look at the number of conjugating system. Because there is a presence of number of conjugating system and also there is a presence of lone pair of electrons on oxygen, definitely we can see that there is a pi to pi star transition. Obviously I can also observe pi star to pi transition. Now I can also observe, because there is a presence of lone pair of electrons, I can also get n to pi star transition. So obviously I can also observe pi star to n transition. So in such a molecule where there are n number of conjugating double bonds and lone pair of electrons, we can expect that there may be a presence of fluorescence and phosphorescence. So basically fluorescence is observed from less energetic transition, which will occur either at pi star to pi or pi star to n transition. In pi star to pi or pi star to n, whichever requires the least energy, that shall happen. Either it can be a fluorescence or it can be a phosphorescence system. Coming to structure. Now whether the structure of the molecule shall influence the variables affecting the fluorescence and phosphorescence, yes, definitely the structure of the molecule shall affect. The most intense fluorescence is found in compounds containing aromatic group with lower pi to pi star transition. A few aliphatic, alicyclic, carbonyl and highly conjugated double bond structures also exhibit fluorescence as well. But most of the unsubstituted aromatic hydrocarbons, they fluoresce in solution too. The quantum efficiency increases as the number and the degree of condensation increases. Simple heterocycles such as the structures that I can see, they can be pyridine, pyrrole and some other structures, they do not exhibit fluorescence. Now in this particular explanation, as I have already told, the fluorescence effect will increase if the structure is more kind of a rigid structure. That means if it is a Benz fused structure, then the fluorescence shall happen. If there is a simple heterocycle like pyridine, furan, thiophene and pyrrole, fluorescence shall not happen. This happens because there would be very less pi to pi star transition in unsubstituted simple heterocycles, whereas there is a substituted heterocycles like quinoline and isoquinoline, which are Benz fused and they have lot of conjugated double bonds. In turn, they can easily give me pi star to pi transition and they can give me pi star to n transitions. Now in this way, benzene ring substitution causes a shift in the absorption maxima of the wavelength and changes in fluorescence emission. Now once the benzene gets fused with the system, we can easily observe the system of more amount of fluorescence that shall happen. Now generally it is observed in aromatic compounds. Why it should happen is because pi star to pi transition can easily happen. The quantum yield increases with the number of rings and the degree of condensation. Now this means that if I consider naphthalene, anthracene with benzene, obviously naphthalene and anthracene will have a more amount of fluorescence compared to that of benzene. This is because they have got more condensing capacity. Now it is observed that fluorescence is generally favored for very rigid structures. That means the structures where lot of rings are involved. Fluorescence increases if there is a chelating bound agent. That means if there is a metal through which these rings get chelated, then the fluorescence always increases. Now when there is a very low energy of pi to pi star transition, where we can observe in an aromatic system, there will be always an intense fluorescence. Heterocycles which are not fused with a benzene ring do not fluoresce. Heterocycles, if they are fused with a benzene ring or any other ring, then easily it can fluoresce. But in a heterocycle, hetero atom is present. Now if there is a presence of a heteroatom, then it increases the intersystem crossing. Then obviously there will be a phosphorescence that shall happen. Conjugated double bond structures, they also exhibit fluorescence. Now they can be an example like lycopene, which is again giving me a fluorescence. Obviously when it can give me a view visible spectroscopy, it can also give me a fluorescence, because lycopene has got 11 conjugated double bonds, which is found in the tomatoes. Now when I see these structures, if there are heavy atoms like fluorine, bromine, chlorine, now if there are heavy atoms such as iodine, bromine, then intersystem crossing takes place. As a consequence, fluorescence decreases. Now this particular phenomena, it is called as heavy atom effect. This in turn actually decreases the fluorescence. That means if there is a heavy atom effect, obviously there may be a presence of phosphorescence and the presence of fluorescence may decrease. Now influence of a halogen substitution decreases fluorescence as the molar mass of the halogen increases. Once the molar mass of the halogen increases, then the fluorescence decreases. This exactly is an example for heavy atom effect. Now this suggests that the probability of the intersystem crossing increases as the size of the molecule increases. So we can see that if there is a presence of iodobenzene, if there is a presence of bromobenzene, they give me an heavy atom effect. In turn, they shall not give me fluorescence, but rather they shall give me a phosphorescence system. Now in case of heavy atom substitution such as nitrobenzene, iodobenzene, they might undergo a pre-dissociation. That means the nitro group can be cleaved off, the iodo group can be cleaved out. In this way we can say that once they get cleaved off, then there may not be a fluorescence system. Now if there is no fluorescence system, that means there may not be any fluorescing activity that we can observe. Now if I go on increasing the substitution of benzene, now look at this, benzene, toluene and propylbenzene. What did I do? I have just go on substituting benzene. 2 benzene I have added to 1 methyl group and I have added an ethyl group in case of propylbenzene. So in this way, if there is a benzene ring substitution, it causes a shift in absorption maxima of the wavelength and changes in fluorescence emission. Benzene is substituted with increasing methyl addition, the relative intensity of fluorescence increases. That means once we go on increasing the type of substitution of benzene, then the intensity of the fluorescence goes on increases. So increase in the ring substitution increases with the fluorescence effect. Now fluorescence increases as the oxygenated species increases in substitution. Now we can say that if there is a presence of phenol, there is an anisole, there is a presence of phenolate system, the relative intensity of the fluorescence increases if there are more oxygenated species and they are present in the substitution. The values of such, they always give more fluorescence. Now this is because phenol is less than anisole, which is less than phenolate ion. Now phenol, the lone pair of electrons on oxygen, they are involved in the conjugation, hence the fluorescence will be less. Whereas in an anisole, it is an electron donating system and the benzene pi to pi star, in turn pi star to pi increases and there will be more fluorescence. Once there is a phenolate ion, after the abstraction of the proton, there will be lone pair of electrons which are associated with the oxygen. If there are presence of this lone pair of electrons and the negative charge, this actually increases fluorescence, and sometimes because of the intersystem crossing, it shall also give me phosphorescence. That means it can give me pi star to pi or pi star to n transition. So this is the effect of the structure. Coming next to structural rigidity. Previously when I told about structure, I always said that if there is a presence of some kind of structural rigidity for the compound. Now for example, we can see here 8-hydroxyquinoline, it is chelated to zinc. Once such a structural rigidity increases, that means there will be increase in the fluorescence. Now for example, quinoline, which is Benz fused pyridine system, and there is an indole, which is Benz fused pyrrole system. There is a fluorine system. There are two benzene systems which are attached to cyclopentane system. Now these structures are highly rigid structure. Increase in the structural rigidity increases the fluorescence system. This is because the concept of rigidity is used to explain the increase of fluorescence, because once there is a kind of a chelating agent, the fluorescence intensity always increases. Now fluorescence is particularly favored in molecules with very rigid structures. Quantum efficiency of fluorine system, there may be biphenyl system, there may be a system like quinoline indole system, which are said to be Benz fused, they will show more fluorescence. The difference is that fluorine system is a more rigid system than that of some other systems that we are going to look. Now, increase in the structure rigidity increases the fluorescence. But when I speak about structural rigidity, now if I compare naphthalene or fluorine versus biphenyl. Now let us compare this fluorine versus biphenyl. Now if I see, fluorine here is more rigid than that of biphenyl, because biphenyl still the systems are just connected with one single bond and the rigidity is very less, whereas in the fluorine structure two benzenes are fused with a cyclopentane structure. Now this increases the rigidity. Now if I compare fluorine and biphenyl, fluorine will have more fluorescence compared to that of biphenyl system. Rigid fluorine has higher quantum efficiency than an unrigid biphenyl. Now higher quantum efficiency meaning what? There will be higher fluorescence. This indicates that fluorescence is favored in rigid molecules than that of your unrigid molecules. Yeah. Before I move on, the explanation for lower quantum efficiency or lack of rigidity is caused by the enhanced internal conversion, which increases the probability that there will be radiational-less deactivations. Now why does biphenyl gives very less fluorescence is because it is already a very weaker rigid structure and it enhances radiational-less deactivation. Non-rigid molecules can also undergo low frequency vibration, which accounts for the energy loss. That means if there are non-rigid molecules, they shall lose lot of energy, and in turn because of this loss of energy, there would be very less fluorescence. Whereas in the rigid molecules, the energy is actually held upon the molecules so that the fluorescing system or the fluorescing capacity increases. So in turn, molecules with rigid structure fluoresce to a higher extent. CH2 in fluorine enhances the structural rigidity. In turn, we can say that it is a highly fluorescing molecule. Now coming to the temperature effect. Decrease in the temperature increases fluorescence. This is because there will be deactivation. That means if I go on increasing the temperature, then there will be lot of collisions. If I go on decreasing the temperature, then the collision shall decrease. In turn, if there is a decrease in the collision, then obviously there will be increase in the fluorescence. Increase in the fluorescence intensity with decreasing T, that is reducing in the deactivating collisions. Once the temperature decreases, then the collisions between the molecules decreases, in turn they fluoresce easily. Now quantum efficiency of fluorescence decreases with increasing temperature. That means if I go on increasing the temperature, the fluorescence is also going to go on decreasing. If I go on decreasing the temperature, the fluorescence increases. Now as the temperature increases, the frequency of the collision increases, and with increase in the probability of the deactivation by external conversion. Now external conversion meaning what? The molecules shall go on losing energy due to collisions between them. Solvents with various types of system will help this system. Now in case of temperature, if I decrease the temperature, there will be increase in the fluorescence. If there is increase of a temperature, then the fluorescence activity decreases. That is the effect of temperature. Coming to a solvent effect. Solvents with lower viscosity have higher possibility of deactivation by external conversion. That means if there is a lower viscosity, then there will be deactivation by external conversion. That means the molecules will give their energy to the solvent system, and hence there will be radiational less deactivation. To avoid this, what we have to do? We have to increase the viscosity of the solvent. If we increase the viscosity of the solvent, there will be an increased fluorescence. This is also because increase in the viscosity of the solvent, there will be less collision. Fluorescence decreases when the solvent molecules are heavy, like carbon tetrabromide and ethyl iodide. Now this is because of the inter-system crossing that is going to happen. Now previously in our structure we saw that if there is a bromide system or an iodide system, rather than fluorescing, there will be an inter-system crossing. Now if the solvent is also of that quality, that is carbon tetrabromide and ethyl iodide system, then rather than giving a fluorescence, it shall give me phosphorescence system. So this is how solvent effect is. If I want a stronger fluorescence effect, I should have an increased viscosity, so there would be less collisions. Now if I make use of a very heavy solvent like carbon tetrabromide and ethyl iodide system, rather than giving me a fluorescence system, it shall give me a phosphorescence system. So this is the effect of solvent in the variables. Thank you.